Happy Steel Day and welcome to AISC's live webinar, 50 Tips for Designing Constructible Steel Buildings, presented today by Clifford Schwinger. My name is Brent Liu. I am with AISC's Continuing Education Group, and I will be moderating today's presentation. I want to introduce today's speaker, Clifford Schwinger. Clifford Schwinger, PE, is Vice President and Quality Assurance Manager at the Harmon Group in King of Prussia, Pennsylvania. He graduated from Lehigh University in 1976, serves on the AISC Manuals Committee, and has more than 30 years of experience designing building structures. We're very pleased to have Mr. Schwinger here today to present. Thank you, Cliff, for being here, and I'll hand things over to you.
Okay, thank you, Brent, and thank you, everybody, for signing up for today's webinar, 50 Tips for Designing Constructible Steel Buildings. As Brent said, I have about 30 years of experience at designing building structures, and over the years I've made more than my fair share of constructability flubs, if you will, on projects that I've worked on. And much of what I've learned has been learned the hard way by making mistakes and getting phone calls from contractors and fabricators and having to spend extra time fixing those mistakes and addressing the concerns. Constructability is something that's not taught in school. It's learned on the job. But hopefully through more seminars such as this, engineers will be able to learn about constructability the easy way without having to go through the pain of answering RFIs and answering phone calls from fabricators and contractors. There's a growing awareness in our profession that constructability is an important topic that we all need to be aware of and learn more of. And hopefully today you'll learn some tips that you'll be able to start using right away when this webinar is over. The nice thing about constructability is that every one of the tips that we're going to be going over today is not only going to reduce the cost of the structures that you design, but they're going to also make your job easier. Less effort spent during design, fewer phone calls during construction, fewer RFIs, and less time spent redoing things to fix problems. Constructability can really be considered the art of structural engineering. If you look through all of the slides or the handouts, you'll see there's no calculations anywhere. It's all a matter of judgment and balancing one detail versus another detail. There's not always one right answer to constructability challenges. As engineers, we always like binary answers, yes, no, right, wrong, but with constructability, that's not the case. These tips are not rules, and there's exceptions to every one of them. Consideration of constructability is a balancing act. Solving one problem might create another. In general, I don't like to use the word mistake when talking about constructability mistakes. I prefer constructability challenges. It's a more appropriate term. In general, constructability challenges don't compromise safety, but they can. I think most structural engineers are aware of that skywalk collapse. I think it was in the 80s in Kansas City. And I was just thinking about this the other day, and I think that that collapse may have been precipitated by the engineer or designer designing that skywalk with a detail that had constructability issues. The fabricator or somebody along the line changed the detail, and there was a subtlety, a shift in the load path that resulted in the skywalk collapsing. More often than not, constructability challenges don't compromise safety, but they do add cost. So it's something that we all have to be aware of. Engineers also have to be aware of the fact that just because you can model a structure in your computer does not mean the fabricator can easily fabricate the steel or the erector can easily erect the steel. In today's economy, engineers are being challenged ever more to design the most economical structures possible. We're using strength design to squeeze as much capacity as we can out of our steel framing. We're using higher strength materials, and we're using sophisticated modeling techniques to take all of the fat out of our design. However, sometimes it seems that the more modeling we do, the heavier the structure gets, but that's a different story. Consideration of constructability provides another essential tool that engineers can use in order to reduce the cost of their steel frame structures. Finally, before we get into the tips, I just would like to point out that my focus today is to focus primarily on steel frame structures where R equals 3 for seismic design. Some of these constructability tips may not be valid for structures where R is greater than 3 and structures where we have to use AISC 34110, the seismic provisions for structural steel buildings. So if you see anything that looks like it's not appropriate for an R greater than 3 structure, that may be true. I'm focusing on R equal 3 buildings. And even for R greater than 3 structures, most of these tips still apply. Keep in mind that these tips are only suggestions. The building code does not mandate that engineers design constructible steel frame buildings. There are often several good solutions to most engineering problems, and the best solution might vary around the country depending on local construction practices and contractor preferences. Finally, the best design is one that provides steel fabricators with options and flexibility. So what is this term, constructability? I don't think it existed 30 years ago, and I seem to remember starting to hear the term mentioned about 15 years ago. And I think it was in response to the advent and widespread use of engineers using computers to model entire structures and then taking those analytical models and putting them in the building information model. And there was a focus away from paying attention to the details as to whether the structure could actually be fabricated and built. As I said earlier, just because you can model a structure does not mean the fabricator can economically build it. Also, it's not just about the tonnage of the steel, it's about whether the pieces can be economically connected together. There are 4 principles of constructability. First, simplicity equals economy. The more simple a structural frame is, the more economical it will generally be. Second, least weight does not always equate to least cost. I think AISC has been talking about this point for about 25 years. I remember going to a seminar in the 80s, an AISC seminar, where this fact was mentioned with regards to designing columns. They were saying, select a heavier column and eliminate the stiffeners, and that will be a lower cost structure. We'll talk about that later. Third, the fewer the number of pieces, the greater the economy. And finally, the executive summary of my presentation today, it's all about the connections. The more efficient our connection design requirements are, the lower the cost of the structure will be, and the more constructible it will be. You'll notice that each one of these constructability tips doesn't have the word constructability in it. They all have economy or cost. They're really one and the same. With that, let's go over our tips. Tip number 1, if you remember only one tip today, I hope it's this one. Show the reactions. Why? Because a significant percentage of the cost of a steel frame structure is in the connections. Excessively conservative connection design requirements do not enhance safety. Think about it. When we design beams, we calculate the loads, we compute the moment, and we select the beam size. Let's say we design a beam and we select a W14 by 22. Are we going to arbitrarily increase it to an 18 by 35 for no good reason other than, well, I think I'll just make it a little bit heavier? Of course not. But with regards to connections, many engineers don't think twice about requiring connections to be designed for 2, 3, 4 times more than they really need to be per the building code. I asked an engineer several years ago, an engineer who works for a large steel fabricator, and he's a well-respected and well-known fellow. I said, what percentage of the cost of a building structure is in the connections? And he said, well, think about it. The steel fabricator buys the steel from the mill that comes into the shop. And then most of what's done with that steel afterwards has to do with the connections. The steel's detailed, connections are detailed, the connections are fabricated, holes are drilled, beams are coped in the shop, the steel's shipped to the field, and then everything's connected together. When you look at the cost of the finished product and you subtract the cost of what the fabricator paid from the mill, what happened in between? It was all about the connections. Most of that cost was in some way or another related to the connections. So I think a ballpark figure is about half the cost of a steel frame building is in some way or another related to the connections of the structure. So if we as structural engineers mandate the connections be designed for twice what they really need to be, we will be adding a substantial cost premium to that structure. I'm going to be going over some notes that I've seen over the years on other engineers' drawings. And just to back up for a second, about 5 years ago, we started designing connections for steel fabricators. Traditionally, our clients have been architects. We worked as the engineer of record designing building structures. But about 5 years ago, a fabricator approached us, and we started designing connections for them. And it's been an incredibly educational experience because it's given us the opportunity to see design documents produced by engineers from all over the place. And we've seen a number of trends on those drawings. And I'd like to point out, and not all of them being good trends with regards to constructability, I'd like to point out some of the things that we've seen that I think engineers could benefit from if they make some changes to their drawings. If you recognize any of these notes, you can rest assured that I probably didn't see your drawings because all of these are widespread. These are notes that I've seen over and over on many different engineers' drawings. It's a trend, and hopefully we can reverse that trend so that steel frame construction can be ever more economical. This is probably the worst note, if there is such a thing. Connections shall be designed to support the full shear strength of the member. Usually, the reaction at the end of a beam is only a fraction of the shear strength of a member. Requiring fabricators to design and detail connections to resist the full shear strength is wasteful and inefficient. As soon as you cope the beam, you're going to start losing shear strength and punching holes. And with grade 50 steel, there's a little bit less forgiveness with regards to rupture strength because the ratio between tensile strength and yield strength is much lower than it was for A36 steel. So designing a connection to resist the full shear strength of the member is not easily done. More common is a note such as this. And I'll bet that 80% of all engineering firms in the country, at least on the East Coast, rely on one way or another on table 3.6 in the steel manual. Many engineers have a note similar to what I have highlighted here on this slide. Connections shall be designed to support the reactions occurring from uniform loads equal to 150% of the uniform load capacity of the beams from Table 3.6 in the steel manual. This note is usually excessively conservative, but sometimes can result in connections that are dangerously under strength. Let's look at an example. Here's a W24 by 76 transfer girder. From Table 3.6 in the steel manual, the uniform load capacity for a 40-foot span is 150 kips. If an engineer were to specify a requirement that the connections be designed for a reaction of 150% of the uniform load capacity, that would be a 113 kip reaction at each end, or a required connection design strength of 113 kips at each end. You can see at the left end, we would have a connection strength twice as big as we need. But at the right end, we're close to where we have that concentrated load. We're under strength by a factor of 100%. We have a reaction of 234 kips, and we're going to get a connection that's only good for 113 kips. That's danger territory with regards to connection strength. Some engineers have realized this, and they've modified their note. They've added a sentence: the effects of concentrated loads near an end reaction shall also be considered. So how's a fabricator going to consider the effects of concentrated loads near the end reaction of a beam? They're going to send an RFI asking for the reactions. So save yourself some time and just show the reactions on the drawings before they're issued for bid. In addition, where you have moment connections or axial loaded members, show the required connection strength for the moment connections based on the actual applied moments, and the axial loads in hangers, drag struts, braced frames, and truss members. If we design our connections for the actual reactions, whether they're factored or ASD reactions, whether we're using ASD design or LRFD design, we're going to have a safety factor of about 2. That's an adequate level of safety, and that's comparable to the level of safety we have when we design beams for flexure. In fact, it's even greater. I believe the safety factor for beams is about 1.67, so for connections it's about 2. There's no need to require connections to develop the full capacity of the section unless it's required to do so by analysis or by the building code. As I said before, when it comes to seismic design where R is greater than 3, there is a need to design our connections for loads that are close to or even greater than the capacity of the section. Likewise in progressive collapse design, but that's not what we're talking about today. We're talking about the more routine building structures, gravity loads, wind loads, and seismic loads when R equals 3. In addition to showing the loads, we should also show the load combinations and the directions of the reactions, forces, and moments. Another note we see on the drawings quite often is a requirement that the connections be designed to support the loads, the shears and moments and axial forces in any direction. Well, that's also a wasteful requirement, unless, of course, the moments and shears can occur in any direction. I have 2 details shown here. One detail I have, both of them are beam to column connections. On the left, I have a negative moment framing in on the left-hand side, and there's a smaller positive moment that's countering and reversing that negative moment on the right-hand side. This is a condition that you quite often have in a building with some lateral loads. This may be a wind moment frame. You have gravity dead loads, and depending on the direction of the wind, there might be some reversal. Well, in a situation like this, you're probably not going to need web doubler plates. You may need stiffener plates. I don't have the stiffeners shown. You may need the stiffener plates if you didn't size the columns to avoid the need for stiffeners. But let's take a look at the detail on the right. On the right, the engineer specifies that you have to look at the maximum moment occurring in all directions, and then add to this requirement the note that's often accompanies it to design the connections for the full strength of the member. In that situation, you're undoubtedly going to need doubler plates and probably stiffener plates. The cost of the connections in detail 2 are probably twice that of detail 1. So unless the load combinations acting in all directions really do occur in all directions, don't mandate that the fabricator consider loads in every direction if they don't actually occur in every direction. Tip number 4. Require connections to be designed per the requirements of the building code, AISC 36010 and AISC 34110. Now, you're looking at that tip, and I'm sure many of you are wondering, how in the world is this a constructability tip? Require the connections to be designed per the requirements of the building code? Well, what I'm saying is, don't make up your own connection design requirements in excess of what's in the building code. I'm going to go over some examples now, and these are examples that we see all the time. Allow the use of bearing bolt strength values where permitted by the building code. This is a note that's not uncommon that we see. All bolted connections shall be designed as slip-critical connections. Slip-critical connections are generally only required when we have oversized holes or when we have slotted holes that are used with loads perpendicular, with loads parallel to the slots. If you have a slotted hole and the load is parallel to the slot, you need a slip-critical connection. Otherwise, we can usually use bearing bolts. Now, there are other situations where slip-critical connections might be appropriate even for standard size holes. That may be in a splice on a long span member where we have large moments. Let's say we have a transfer girder 150 feet long and we have a splice near the midspan. The fabricator, well, if we were designing that, we would probably opt for either a welded moment connection, a welded splice connection, or a bolted splice connection with oversized holes and slip-critical bolts. But even if we were to use a bolted connection with bearing bolts and standard size holes, you might find that there may be a little bit of too much deformation in the connection to warrant the use of bearing bolts. So there are some situations where slip-critical bolts are appropriate, but for the majority of connections, bearing bolts are perfectly acceptable. This note is not quite as bad as the one on the previous slide. It's a note saying the following connections must be slip-critical. And then there's a whole menu or a whole list of where the engineer wants slip-critical connections. But the bottom line is that in most of these situations, bearing bolts in standard size holes or bearing bolts through short slotted holes with the load perpendicular to the slot would be perfectly acceptable. Now, the bolts may have to be pre-tensioned, and I think that's where some of the confusion is coming from. Let's look at this section of the specification. And actually, I just revised this slide from the previous slide that I had was based on AISC 36005. In 36005, this note said joints with pre-tension bolts, slip-critical bolts, or welds shall be used for the following connections. AISC has deleted the slip-critical, and the important requirement is either pre-tension bolts or welds shall be used in these connections. And here's a list: column splices in tall buildings, connections of beams to those columns in tall buildings, structures carrying heavy, larger cranes, and connections for the support of machinery and other live loads that produce impact or reversal. The bottom line is I think the confusion that some engineers have is they use the term pre-tensioned and slip-critical interchangeably. All slip-critical bolts are pre-tensioned, but not all pre-tensioned bolts are slip-critical. Do not use the term interchangeably. The advantage, a pre-tension bolt, you can use the bearing bolt strength values. A slip-critical bolt, you have to use much lower shear strength values. If that previous slide wasn't enough to convince you as to the validity of using bearing bolt strength values, let's look at AISC 34110, section D2.2. The print's a little small here, but the gist of the note, or the gist of the specification, is that even when we're designing structures where R is greater than 3, structures that could be in high seismic regions, we're still allowed to use the shear strength value based on bearing bolt connections, as long as we have standard size holes or short slotted holes with the load perpendicular to the slot. Now, 34110 does require that the bolts be pre-tensioned and that the faying surfaces be prepared as you would for slip-critical connections. But the bottom line is the bolts are designed as though they were bearing bolts. If you have oversized holes, or if you have slots with the load parallel to the slot, you must use the slip-critical value. Otherwise, bearing bolt capacities are usually acceptable. Tip number 6, permit the use of one-sided connections, that is single angle or single plate shear connections. This is a common prohibition on the drawings that we see when fabricators give us drawings to look at for connection design. Many engineers, for whatever reason, prohibit the use of one-sided connections. This note, this is an example of a note of the grammar is really lacking. I think there's a lot of issues with this. Avoid one-sided connections if possible, and do not use for beams deeper than 18 inches. But if you have to use a one-sided connection, design it in accordance with the manual. Usually the notes are a little clearer. They just say no one-sided connections. The problem with that is there are many situations where fabricators don't have much choice. Skewed beam connections. A skewed beam connection really requires a shear tab or bent plate connection. Fabricating and erecting, fabricating a beam with a double bent plate connection, in other words, a double angle connection where the angles are bent, a bent plate, is usually impractical and unconstructable. Shear tabs have been used, I'm just guessing, probably in thousands of buildings. I would venture to say there are hundreds of thousands of single angle and shear tab connections that have been safely used and successfully used in buildings around the country and around the world. I know of no instances anywhere where a properly designed one-sided connection has caused any problems of any sort. AISC and the steel construction industry have spent a lot of time researching these connections, and there's a lot of data that supports their use. So engineers, if you have a note similar to this on your drawings, you should take it off the drawings, and just because what you're going to do is you're going to get an RFI from a fabricator saying, look, how do we connect this beam? Can we use a one-sided connection? So rather than waste the time and answering unnecessary RFIs, just allow the use of one-sided connections. They're safe and economical. Permit the use of any size and type of bolt. This is another note we see all the time. All bolts shall be 3/4 inch diameter, all holes 13/16. Allow the fabricator to determine the bolt size and type especially when you're delegating the design. Now, if you're detailing every connection on your project, well, perhaps a note like this would be valid. But quite often what we see is this is just a standard note that's thrown on the general note sheet, and it's unnecessary. The second half of that requirement, all holes shall be 3/16 inch diameter. Engineers shouldn't arbitrarily require that all holes be standard size. Most fabricators require those short slots and shear connections to accommodate tolerances and facilitate erection of the steel. If you've cambered your beams and you require standard holes at each end, then the fabricator or the erector is not going to be able to bolt those beams into position. Those short slots are needed to accommodate that ever so slight rotation at the end of the beam due to the camber. The camber, the tolerances, the differences in temperature from when the steel was fabricated in the shop and when it was erected. AISC connection design procedures permit the use of short-slotted holes with snug-tightened bolts for most types of shear connections. This is a very important point. You know, engineers by nature are conservative, but you can rest assured that the connection design procedures that have been established by AISC have been tested and are safe, and engineers should not go above and beyond and mandate requirements above and beyond what's in the building code. Doing so is wasteful and inefficient. Here's a tip that will save most engineers a lot of time. If you're designing all of your connections, consider delegating design of the connections to the fabricator. AISC 30310, the Code of Standard Practice, has recently formally recognized this. It's been done for years, but it was never formally recognized by AISC. At our firm, for the last 25 years, we've always designed our connections. It's only been in the last several years that we started delegating. It's interesting, when we finally stopped designing all of the connections on our projects, we started designing connections for fabricators. It's common practice now, and delegating the connection design offers many advantages to both the engineer and the fabricator. But if you do delegate the connection design, you should do so properly. Don't delegate that the fabricator design the connections and then give them unrealistic connection design requirements. Give them restrictions concerning the types of connections that are permitted, and give them data concerning the loads. In other words, the reactions, shears, moments, and axial forces. Make sure it's clear as to whether your forces are LRFD or ASD level. And require or make it clear as to what you require as far as submittals. Here's a possible note. You could come up with your own note, but this is just one possibility of a note for delegating connection design. Structural steel connections shall be designed in accordance with the requirements of the building code and AISC 36010 using connection design procedures documented in publications such as the Engineering Journal, Steel Construction Manual, and the Steel Construction Manual Design Examples. Note the words such as. Every possible permutation and combination of connection is not documented in these three publications. Connection design is part art as well as science, and the typical connections, you will find all of your typical connection design examples in this publication, the AISC Steel Construction Manual Design Examples. However, there are always going to be some unusual connections that may not be in these publications, and engineers should be flexible and listen to the recommendations of the connection design engineer who's working for the fabricator. Tip number 10, frame girders to flanges, column flanges, and frame beams to column webs. Girders usually have heavier reactions than beams, and quite often, because of the heavier reactions, the fabricator is going to want to use double angle connections. It's easier to frame a girder with a double angle connection to the flange than it is to the web because, number one, you're not sharing bolts with the girder on the other side, and number two, because the girders are typically much larger members and it's easier to bolt or to position the girder against the flange than it is to finagle the girder between the flanges of a column. Beams, on the other hand, are usually smaller members. The reactions are smaller, and you can usually accommodate those reactions with single-angle shear connections. So look at this detail. It's easy and safe to erect. There are no shared bolts, and there are no copes. An engineer who works for a fabricator one time asked us, do you actually allow the use of single-angle connections to the webs of columns? And our answer was yes, as long as they're properly designed. There's nothing wrong with single-angle connections to column webs. I know the concern was probably the bracing of the column by the beams, but this column with 4 members framing into it is adequately braced, also considering that there's usually a floor slab. Size columns to eliminate the need for stiffeners. Here we have a detail where we have some stiffeners shown, and we see this beam framing into the column web. If we have this condition at both ends of the column, we won't be able to install the beam. It's unconstructible. The fabricator will probably opt for an extended shear tab connection. However, this type of connection will probably require more bolts and a heavier plate. It's probably going to be a little bit more expensive than a standard shear tab connection. Where you can avoid stiffeners, make the opposing beams the same depth. Square stiffeners are less expensive than skewed stiffeners. And if you made this beam deeper, you might not even need the stiffeners. Use the deepest practical column size. I'm not advocating the use of W14 columns for every building, but I'd like to point out that when we have W14s, there's no need to stagger the bolts in the single or double angle connections. W10s and W12s can accommodate single and double angle connections, but we have to stagger the bolts. Avoid W8 columns when you have connections to the web. It's extremely difficult and unconstructible. You can get those connections in, but it's not a standard connection. Avoid W8 columns with connections to the web. Orient columns to minimize the number of skewed connections. On the left, 3 skewed connections, 1 square connection. On the right, 3 square and 1 skewed. Skewed connections are more expensive than square connections. Now, here's where we get into the gray area, because there are some situations where you might want to keep this configuration. When we have braced frames, never orient your columns on a braced frame so that the columns are skewed. Always orient your braced frame columns square to the braced frame, preferably to the flanges. You can easily do the connections to the web, but in any case, avoid braced frame connections or braced frame configurations with skewed columns. The reason being, they're pretty complicated to begin with. So this is a typical brace frame connection with wide flange braces to the flange. So you can imagine how complicated it would be if it was a skewed connection to the web. This will give you some idea. When you have members with large reactions, frame those members square to the columns, preferably to the flanges. Here's an example. We have a W36 by 150 with a 490 kip reaction. 3 connections. A square connection is a standard double angle shear connection. A skewed connection to the flange, well, now we need a skewed shear tab with a weld, either a fillet weld or, depending on the skew, possibly a groove weld. That's possibly a bit more expensive. It's a bit more expensive not because it's welded, but just because of the complexity, the labor involved in detailing and precisely aligning that plate and welding it up. And finally, here's a skewed connection to a column web. Look at this, a 1-inch grade 50 plate with 40 bolts and a CJP weld. This standard double angle connection is much less expensive than the skewed connection to the web. Configure framing so that no more than one beam frames into any one side of a column. This looks perfectly innocent on the BIM model. However, when we look at the detail up close, you can see how complex it gets. We have a large cope in the skewed beam, some possible web reinforcing, and two non-standard connections to the column. Frame only one beam into any one side of a column. Head off steeply skewed connections. If you have a steep skewed connection, especially one with a big reaction, consider heading it off as I show here. Even though you're adding a piece of steel, you're reducing the complexity of that steep skewed connection. Configure your framing to minimize the number of skewed connections. Here we have two bays. All I'm pointing out here is this bay on the left, we have a skewed connection on each end of the beams. On the right, we have a square connection at one end and a skewed connection at the other. Now, here's where the shades of gray come into play. There might be situations where we might want to keep this. This may be a steep skewed connection that we want to avoid. So there might be situations where this is the appropriate bay configuration. Likewise, if this is the appropriate bay configuration, make sure that this member is not too close to this girder to column connection, or you can have some interference here. Likewise, rotate this column in the corner so that we have one square connection and one skewed connection. Favor pipe columns over square or rectangular HSSs when you have skewed connections. The nice thing about a pipe column is every connection is a square connection. Watch out for connection interference where beams are slightly offset from the columns. Again, you look at the BIM model, the analysis model, and there doesn't appear to be anything wrong with this. But then when you go to look at the connections, this is an impossible situation. Increase beam depths to avoid the need for web reinforcing. Situations could include large copes with heavy reactions, high beams framing into low girders, or skewed beams with long copes. There's a possibility that rather than having to reinforce of this W14, if you just make it a W18, you have a much simpler connection. Beams with flange bolted moment connections must have sufficiently wide flanges in order to install the bolts. The minimum gauge for 7/8 inch bolts is 3.5 inches. Whenever you have a W12 with a flange plated moment connection, you have to use at least a W12 by 26. So even though a 12 by 19 might work, you won't be able to get the bolts into the flange. Size members to have sufficient strength at the net section. The rule of thumb is that we should never take our tension members in braced frames and trusses to more than 75% of their yield strength capacity, because what's going to be problematic are the connections, especially with the higher strength steels. And if engineers always want to design the least weight, most efficient structures, so they'll look at their analytical model and they'll take those members right up to the max. But the trouble now is when you delegate that connection design, the fabricator's engineer is going to have an impossible task of accommodating that, designing that connection without having to reinforce the section. So we're about halfway through, so now I'll take some questions if anybody has any questions.
Okay, thank you, Cliff. We do have several questions. I would like to have you address some of these before we move on. The first question is, and I think it's a pretty general question, but I'd love your insight on it. Which of the two is more cost effective? Delegated connection design or connection design by the EOR?
Delegated connection design. The reason is all fabricators are going to have their own preferred connection details, their preferred bolt diameters. Some fabricators we work with they like using 3/4 inch diameter bolts. Other fabricators and erectors, they want to use 7/8 inch diameter bolts. If you allow the fabricators to use their preferred connection, then the owner will get the most economical steel structure.
Okay. That's probably a good segue into another comment that was made. This person's comment is, if you allow this fabricator to specify material and diameter bolts, there's a greater chance of mistakes in the field. Do you agree? For example,
no, I don't agree.
Mixing up a 325 bolt with an A490 of the same diameter.
No, well, you know what? Most fabricators are savvy enough not to do that because of just that problem. Most fabricators will opt for one standard bolt type and diameter for the majority of connections. Let's say a fabricator says, I'm going to make all of my shear connections, I'm going to make all of my connections with 7/8 inch diameter A325 bolts. Well, when they get to those special connections, the plate girders with the heavy reactions, the trusses with the heavy reactions, chances are they may not be able to use a 7/8 inch diameter A325 bolt. Well, they're not going to go to a 7/8 inch diameter A490 bolt. They're probably going to go up to a 1 1/8 inch diameter A490 bolt. Because if the forces are that much higher, if they're so high that they can't use an economical number or configuration of 7/8 A325s, they're not just going to switch to a 490. They're going to bump up a couple of diameters out to use a larger A490 bolt. A fabricator doesn't want to make a mistake any more than an engineer wants to see a mistake being made. It's not in anyone's interest that mistakes be made in the field, and fabricators are savvy about this and know how to solve these problems.
Okay, thank you. Here's a question, some clarification on using slotted holes. The comment is this: slotted holes are normally used to allow movement along the slot direction. Would not a slip critical connection prevent this movement?
Yes, well, slotted holes are used for a number of reasons, and actually slotted holes generally, to my knowledge, are not used to allow, at least in the connections we don't detail slotted holes to specifically allow movement in the connection. We use slotted holes to accommodate tolerances, temperature differences, to accommodate erection of the steel. If we have a slot in a hole and we have a load parallel, if we have a slot and we have a load parallel to that slot, we're going to design it as a slip critical bolt. And I'm not sure what the intent of the question was. You should never use a slotted hole to allow for expansion and contraction. That's not a good detail. You don't want that bolt sawing back and forth inside that slot. That slot's just there to accommodate tolerances.
Okay. And then here's a couple questions in regards to delegating connection design. If you are designing a structure in ASD, allowable strength design, should you require the connections to be designed in ASD as well?
That's up to you. And I would say, you know what, I would say yes. If you're designing your structure in ASD, then show the ASD reactions. I mean, that's what you're going to be doing. If you're modeling the structure in ASD, you push the button on your computer, you get your ASD reactions. I would be consistent and stick with the ASD or stick with the LRFD. Don't mix them up. It's too confusing. And in our office, to tell the truth, in our office, we use LRFD exclusively because when it comes to constructability, and this is a slight difference, they're both based on strength design, allowable strength design and LRFD. But the advantage of LRFD is that for most structures, you might have a couple, in heavy connections, you might have a fewer bolts in an LRFD connection and an ASD connection. The two methodologies were developed or calibrated based on an average load factor of 1.5. When the average load factor is less than 1.5, LRFD will be slightly more economical. Not that both of them are perfectly acceptable, but I just wanted to point that out.
Okay. Then I'm going to try to combine two similar comments here. But with all of the load combinations required to be considered in design, how do you propose that you effectively convey all the critical reactions? And then further, how do you verify that they've been considered if the design has been delegated?
Okay, well, first off, for most of the connections on a job, this isn't an issue. You know, the gravity connections, gravity moment connections, gravity shear connections. It's only in things like, for instance, braced frames, trusses, and some maybe moment connections in moment frame buildings. And I understand the challenge, but with whatever it is, 150 load combinations, usually only a couple of them flush out to be the governing ones. You have your gravity load combinations, and you have your gravity and lateral load combinations in both directions, and then you have your what I call the empty building load combinations, where you have dead load only. So there aren't as many as you think. And you know, engineers, like I said, I don't want to oversimplify it, but at the other extreme, what we see are too many engineers not putting any thought into it, and just requiring not only that the connections be designed for moments and shears and all reactions, but yeah, just design it for the plastic capacity while you're at it. And that's when the connection design becomes extremely expensive and wasteful. So I understand the pain, because I design buildings every day. I know the complexity of the code, but usually you can flush out most of those load combinations and focus on just a few of the bigger ones. And one possibility is to give the axial loads due to gravity, and then give the axial loads in a braced frame that would be resulting due to the wind loads. Give 2 axial loads. We don't do that, but that's one possibility.
Okay. And then I think one more question before we move on, and we'll have another, just to make sure everyone's clear, we'll have another Q&A period at the end, but we'll address one more question before we move on here. And that is, this person's comment is that I have found that contractors always base their price on total tonnage of the steel, and so lighter columns and beams will be cheaper, regardless of stiffeners and doubler plates that may be required. How do you overcome this problem?
I think in my experience, and you know what, I've often thought the same thing, but you know what, most fabricators do not just look at tonnage. They look at tonnage and complexity. If it's a building that has a lot of repetitive, heavy members, then the cost of the connections is going to be a smaller percentage. But if it's a building that has a lot of complex connections, a lot of light framing members with complicated skewed connections and whatnot, then the fabricator is going to factor in a higher cost for the connections. It's not quite as simple as that. You know, I know most engineers, myself included, we're always asking, what's the cost per ton? What's the cost per ton? Because we want to design the lightest building, the most economical building, but we have to be aware that things that we do, while we're well-intentioned, might be having the exact opposite effect. Fabricators do notice when you have stiffeners at all your column moment connections, and that will be factored into the price.
Okay, and then just for clarity, can you just let everyone know, where can an engineer of record find out what is required to be in their drawings for delegating connection design?
It's in the Code of Standard Practice. I referenced before, I think I had a page from AISC 30310, the Code of Standard Practice. It has all of the procedures and rules for delegating connection design. And you know what? If you're all of you engineers of record out there, if you have any questions, email the Solutions Center. They are the greatest resource. And I'm sure people from the Solutions Center are probably wondering now how many questions are going to start flooding in, but they're a great resource for all of your questions of this nature. And if you have a question could be, I would like to delegate connection design. How do I do it? But for this case, the response will probably be, refer to section so-and-so in the Code of Standard Practice.
Okay. Let's move on, and we'll answer more of these questions as we get to the end.
Okay. Okay, I'm about halfway through now, and this is the first tip that has nothing to do with connections. So that tells you how important connections and connection design is with regards to the constructability of steel frame buildings. Communicate and coordinate. Engineers aren't the greatest communicators in the world, myself included, but we have to learn to be better communicators if we want to be better engineers. Talk to your client if their design is creating inefficiencies. They might tell you that that's what they want, but you have to say something, because if you don't and the project comes in over budget, they're probably going to tell you, you should have told us this 3 months ago. Ask your client in writing for the information that you need, and give them the dates for when you need that information. It's not enough to say, I need to know the column grids. You need to say, I need the column grids by Friday in order to get the mill order package done 4 weeks later. Finally, anticipate what other consultants will be doing in order to avoid coordination problems and interferences during construction. In other words, learn to be a mind reader, because the only people who are worse than communicating than structural engineers seem to be mechanical engineers. This is from an actual project, and there was even a BIM model that showed these beam web penetrations. And here's what can happen when you don't anticipate, coordinate, and communicate. Don't allow the mechanical engineer to box you into this situation. They're not going to tell you about these beam web penetrations. They don't care where your beams are. They're just going to put the ductwork wherever they want it, and whatever happens, you'll make it work. The better solution is for you to anticipate these issues up early on and up front. A possible solution might be maybe this beam might have to be a little bit shallower. It might be heavier, but it's going to be a lot less expensive than having to put a lot of web reinforcing around that big opening. Another solution might be to move this opening to the midspan where the shear is smaller. Another solution might be to use a greater number of smaller openings that don't have as severe an impact on the shear strength of this beam. And secondly, don't delegate the design of the reinforcing around these beam web penetrations. This is not connection design, this is member design. And on the project we were working on for the fabricator, this was delegated to the fabricator to design this. And I think what happened then was that I think the engineer would have realized that this was not a good situation had they designed the web reinforcing, but they didn't, so it wasn't discovered until fabrication. The Code of Standard Practice 30310 is pretty clear that there has to be sufficient information on the drawings to minimize uncertainty among the bidders. The question that I addressed a couple of minutes ago asked about what information does an engineer need to put on their drawings to delegate connection design. Well, this is the second part. This is the information that engineers are required right now to put on their drawings, regardless of whether they're delegating connection design or not. Even column stiffeners, web doubler plates, even when you're delegating connection design, the Code of Standard Practice requires that engineers show where stiffener plates are required, bearing stiffeners, web reinforcing around openings, etc. So, and the reason for this is when a fabricator is bidding a project, they can't give the best price to the owner unless they know if stiffeners are going to be required, for instance. If they don't know, and they won't know if stiffeners are required unless either the stiffeners are shown on the drawings or their connection designer designs everything. Well, the connection designer is not going to design the connections until they get the project. So that's why this information has to be shown up front on the contract documents. Here's another example of delegating something to the fabricator that should not be done. Don't delegate the design of plate girder welds. We see this done all the time. But the problem with this is the fabricator doesn't know what the shear flow is. Only the engineer of record knows that. So unless the engineer of record provides the shear and moment diagrams on the drawings for the plate girders, the fabricator is not going to be able to size those welds. This is a pretty easy calculation to do when you have the shear and moment diagrams. And also, if you do design these welds on your drawings, don't make them CJP welds. Usually fillet welds will be adequate. Size them for the shear flow, and it's surprising how small these welds can be while transferring that shear flow through the flanges. CJP welds are generally unnecessary, and they're more complicated than fillet welds. Even when you're delegating connections, you have to think about how the connections are going to be detailed. Here's a situation we saw. We've actually seen this a couple times, double plate girders. But when I look at this, I wonder, how are you going to make these connections at each end unless you have a large cope in the flanges? And quite often, there's concentrated loads near the ends of these members, and you can't easily cope the flanges. And also, how do you make these connections? If these webs are 2 feet apart, you can't connect them to a W14 column easily. So even when you're delegating the connections, and you know what? I think delegating connections is, what delegation of connection design does is it frees up the engineer to look for all of these other subtleties in their design. So rather than focus on the minutia of the connections in your building, focus on the big picture. Things like, are these beams connectable? Can the fabricator detail these connections economically? Configure your HSS framing to simplify your connections. Rather than have a standard cope-type connection, consider lowering your HSSs and framing them square to the webs of the supporting beams with an end plate and a shim plate to allow it to be rotated into position. Connections to HSS members can be accomplished with shear tabs. There's no need for through plate, single plate shear connections. We see these on occasion. I think this may have been from the early days of shear tab design, but standard shear tabs are usually perfectly acceptable for connections to HSSs. Here are some welding tips to enhance constructability. Strive for downhand or vertical welds. Avoid arbitrarily specifying all-around welds. I know, you know what, I'll admit it, I do it sometimes in my details, but if you don't need an all-around weld, show only the weld that's required. Avoid specifying arbitrary CJP welded moment connections, and favor fillet welds over groove welds. We see these CJP welded moment connections all the time on drawings because, it's the easiest one to design. It's just a CJP welded moment connection, but it's usually it's overkill. It's far more than is what's usually needed. Select efficient diagonal braces. Single angle braces are good for small loads. Double angles usually give the most efficient shear connections at each end because the bolts are in double shear. HSS braces will give you the highest brace strength per pound of steel. And W shapes are good for high axial loads, but some of the connections can be more intricate than the other types. And here's an illustration of each of the three. When you have a braced frame, configure your slopes so that the diagonals are 35 to 55 degrees. This is for braced frames. This is also a truss tip. You don't want to have these diagonal braces at a very shallow skew because this is what the connection looks like. The connection on the right is a lot more compact. You're probably going to get smaller, less plate tonnage, but smaller plates, thinner plates. So avoid steep skews and braces. Verify that the framing can be installed. This happened on a project that I did about 10 years ago. I got a call from the field that they couldn't install the diagonal braces. I thought I was being brilliant using an HSS brace. It was very efficient. And then I got this call, and I didn't understand it. And what it was the way they detailed the connection, it was too tight. The gusset was not too small. it was designed correctly, but they couldn't then rotate the HSS into position. Make sure that your framing can be installed. And I'm using a braced frame as an example. It applies to any type of framing member. Make sure the framing, whether it's a beam, a column, a brace, whatever, can be physically positioned into place. Configure your framing to minimize the number of beams. On the right, we have fewer beams, so it's generally going to be more economical. Fewer beams, fewer connections, and fewer crane picks. Maximize your slab span in order to minimize the number of beams. Here we have 2 bays. They both have 3.5 inches of lightweight concrete over the deck. On the left, we're using an 1.5 inch deck. On the right, we're using 3-inch deck. The advantage of the you just look at it. The advantage of the configuration on the right is that we have fewer pieces, probably less steel tonnage, fewer connections, fewer crane picks. We have more tributary area per beam, so we have a greater live load reduction. We have more mass per beam, so we have less potential vibration issues. And we have a thicker slab on the right than the left, so that thicker slab translates to a deeper total composite beam depth, so we're going to get more bang for the buck out of our composite steel beams. We have a deeper total composite beam depth and a higher moment capacity in our composite beam than we would with a thinner slab. For seismic design, use R=3 whenever possible. There are significant connection and member design requirements imposed when we use an R greater than 3. I think a lot of engineers who aren't familiar with AISC 34110, and to tell the truth, I'm not. Most of our design is done in R=3 territory. We've done some higher seismic design, but for the most part, a lot of engineers are not aware that you can't just specify an R of 6 and think that that's just in the connections. There are member design requirements that engineers must satisfy when you specify an R=6. Another misconception that I see all the time is, especially on the East Coast, a lot of engineers think, well, my seismic forces are small. I'm just going to use an ordinary steel braced frame or an ordinary moment frame. But be aware that these types of lateral load resisting systems, these are not ordinary. The R factor for an ordinary steel concentrically braced frame is 3.25 and an ordinary steel moment frame 3.5. The connections in these systems have to be designed for substantial moments, far in excess of what you've calculated in your lateral load analysis. You have to design them for the strength of the member. So what we do is when we design our buildings, we call our braced frames an R=3 braced frame or an R=3 moment frame. The title for R=3 systems is a pretty long-winded title in ASCE 705 and ASCE 710, so we just refer to these as R=3 braced frames. Also, it's come to my attention that some engineers have a philosophical problem with R=3 on the East Coast. In my opinion there is, if the building code permits the use of R=3, then you should use R=3 when you design your seismic lateral load resisting system. If you have a philosophical problem with that, well, you should probably tell your owner about it before you add $500,000 to the connections on their building, because there's a lot of time and effort went into developing the seismic provisions in the building codes, and a lot of people who are a lot smarter than me spent a lot of time coming up with these requirements and R factors, and all I can say is I'm going to follow the building code, and I would encourage everybody else out there to do likewise and not require things in excess of the building code. That's not going to benefit anyone. Orient columns and moment frames for strong axis bending. The moment of inertia in the strong axis of a W shape is about 2.5 times greater than the weak axis for W14s. The moment frame at the top, all the columns take about an equal share of the shear. When we have weak axis columns in our moment frame, they're going to take less than half the shear that the strong axis columns are taking. When I have a situation with weak axis columns in a moment frame, I'll often give consideration to just deleting those moment connections and throwing that additional moment into my strong axis columns. I now have, those columns may have to be a little bit heavier, and the moments will be a little bit larger, but I'm eliminating 2 moment connections. And generally, you get more connection capacity. You get more foot kips of capacity per dollar spent on a strong axis connection than you do for a weak axis connection. Because again, if you look at the complexity of this versus the complexity of this, for what you get, the strong axis column orientation is where you want to focus your attention. Run heavy moment-connected girders through columns to simplify the flow of moment through the columns. Here's a situation where we have a large dead load moment passing through a column. I call this a pass-through moment. Well, if it's a pass-through moment, just pass the girder through the column. Now, I was told that this violates the seismic specification for buildings where R is greater than 3. So again, I'm just focusing here today on R equal 3 structures. But you can see the difference in complexity between the two. Run cantilevered roof beams continuous over the tops of columns. This situation is much simpler than this condition. And for both of them, make sure that you don't have a ridge or a valley occurring at the column, because that would necessitate a kink in the beam or connection. Minimize the gingerbread. I remember 10 or 15 years ago, I was reviewing change orders at the end of a project with a fabricator, and I said to him, "What's going on here? The owner bought the building at $2,000 a ton, and you're dinging him for change orders at $8,000 a ton." And he said, "Cliff, look at the steel. It's all gingerbread, little pieces of steel." And he was true. All those little pieces of steel cost less money per ton, more money per ton than the heavier steel. So the less gingerbread we have in our buildings, the lower the cost per ton of the steel. There was the question earlier about, well, no, usually fabricators just look at tonnage. No, they look at tonnage and they look at the gingerbread. Here's an example where usually beams are not gingerbread, but here's a situation where we have the deck spanning left to right, and just by turning the deck up at this cantilevered edge, we were able to get rid of 3 beams. So at no additional cost, none of the other member sizes had to go up in size. Avoid skewed beam-to-column moment connections. These, again, look innocent in the analysis model, but they're very difficult to detail. Avoid full-depth stiffeners where possible. Stiffeners usually don't have to be full depth. If you have a transfer girder, you can usually stop your stiffeners above the bottom flange. If you have a heavy member going over top of the column, you can usually stop your stiffeners short of the top flange. And while we're talking about this, when you orient your columns on your transfer girders, you should always strive to orient the columns so that the web of the column is parallel to the web of the transfer girder. And why? Because 80% of the load in your column is in the flanges. You don't want to have 80% of the load in your column dangling over the sides of the transfer girder. So whether you have a transfer girder or a beam over a column, try to orient your columns accordingly. Simplify your base plate and anchor rod details. The least weight solution is on the left. Rectangular base plates, and engineers who do this will usually just specify an edge distance to the anchor rods. The problem with that is every column could potentially have a different anchor rod pattern, which is a recipe for confusion in the field in setting all of the anchor rods. A better solution is to use square base plates and square anchor rod patterns, and to standardize your anchor rod spacing. Don't give a standard edge distance, give a standard spacing for a given size column. All W12s might have a 16 by 16 pattern, 14s might have an 18 by 18 pattern, whatever works. But that way, regardless of whether it's the W12 a W14 by 43 or a W14 by whatever, it's the same anchor rod pattern. When you get to some of the jumbo sizes, you may have to increase these patterns within the W14 family or the W12 family. Some tips for hangers: avoid pipe hangers where you can. Sometimes architects want to see pipe hangers being used to support suspended framing. The best type of hanger is a single angle hanger or a double angle hanger if need be. Try to eliminate the need for stiffeners if you can. Check equation J10.1 to see if you can get rid of these stiffeners. Better yet, orient the connection plate parallel and underneath the web of the supporting girder. Frame only one member to a hanger. Now this can be a precarious detail that you have to pay attention to. Many engineers, myself included, if we have a double angle connection, a double angle hanger, we say to ourselves, well, good, I can frame 3 beams into that hanger, 1 to each leg of the angles. But it's usually easier said than done. Usually the configuration of where the framing wants to be is going to make it difficult to get the perpendicular beam to the leg of the outstanding leg of the hanger. Sometimes you can do it, and if you can, that's fine. But what we often do is we'll just offset the beams so that only 1 beam frames into the hanger. The complexity with that, though, is that you have to now add this reaction to the reaction on this member in order to first check the shear strength in this supporting member, and then design the connection for that total reaction. So be careful if you do this, but it can simplify your connections. Understand fabricator preferences with regards to their preferred connection details. Call your local fabricator, or if they have an open house tomorrow for SteelDay, go visit them. Avoid torsions in W-shaped beams. W-shapes are notoriously inefficient for resisting torsion, so either brace them with kickers or use HSS sections. Camber intelligently. Don't camber beams in moment frames and brace frames. Don't camber short beams or light beams. Do not over-camber. Specify that additional concrete be poured to achieve a level floor, and include that ponded concrete in your design. Don't specify camber less than 3/4 of an inch. Don't specify that camber be measured after erection. We see this note all the time. The specifications will take exception to the code of standard practice. That's not a good idea. Engineers just need to realize that some camber may dissipate, and we just have to deal with it. And finally, compare camber cost to material costs. Call your local fabricator and ask them how much per ton they charge for cambering. For more information on cambering, AISC has a box lunch presentation, and here's the information on how to get to it. So that's it, 50 tips. In summary, to enhance constructability of steel frame buildings, you have to think about the connections. You have to show the reactions, moments, and axial forces. Do not impose arbitrary constraints on connection design. Do not delegate, or do delegate connection design. If you're detailing your connections now, consider delegating connection design. Strive to keep your connections square. Use R=3 for seismic design when permitted. Understand fabricator preferences. Permit alternative connection details. Minimize the number of framing members. Minimize the gingerbread. And finally, communicate and coordinate. And that's the end of my presentation. I'll be happy to hang around for however many questions anyone has. And here's my contact info. If you have any questions later today, tomorrow, or whenever, feel free to contact us. We're located just outside Philadelphia, the Harmon Group. Thank you.
Okay, thank you, Cliff. We have several questions here. We're going to do our best to get through a handful of these before we run out of time. But the first question I wanted to ask is, someone has asked your thoughts on partially restrained moment connections. Are these cost effective?
Connections we usually use, well, on the taller buildings we use fully restrained moment connections. On smaller buildings we use what I call top and bottom flexible angle connections. And these are connections where you have an angle bolted to the top flange and the bottom flange of the beam. They've been used since at least the 20s. The Empire State Building has these moment connections, I've been told. And you just have to be careful if you design them, because and understand what I was always confused about or had a quandary about was, well, if it's semi-rigid, there's going to be some additional drift, and how do I accommodate that? How do I quantify that additional drift? And actually there's a paper on the AISC website that talks all about these connections. I think it's Dr. Gershwinder wrote a paper, and a Return to Simplicity. And I encourage everybody who might be considering or wondering or wanting to know more about these types of top and bottom clip angle moment connections to download that paper. And the issue about deformation was, I think there was a rule of thumb, increase your drift by a factor of 1.5. That's a rule of thumb to accommodate the flexibility of these connections. I know there's some other types of flexible moment connections, but that's the type that we use on our shorter buildings.
Okay. I'm going to go to slide 43. This is tip number 24. The question is this: when you suggest designing members to 75% capacity for connection design, is this the upper limit suggested for all failure modes or just sheer intention? And then additionally, would it be advantage to design all members to 75% capacity?
Okay, yeah, I hope I didn't mislead anyone with this. This slide is primarily aimed at axial loaded members in braced frames and trusses, and to some extent it's aimed at connections where we might have bolted moment connections at each end. It's also, well, that's pretty much it. But it's primarily truss members and braced frame members. And I'm not advocating to only go up to 75% for design of beams or columns or anything of that nature. And the reason for this is the ratio between tensile strength and yield strength for A36 steel was 58 divided by 36. I think it's 1.61. The ratio between tensile and yield for ASTM A992 is 65 divided by 50, 1.3. So what's happening is if you crank a member, let's say you crank a truss member up to its full strength in tension based on the 0.9 AGFY. I'm talking LRFD here. Then when you get to the connection, and if you have a bolted connection, and this is why I'm saying you have to think about how the fabricator is going to connect the steel, you're going to find that if you have this heavily loaded member, you're going to have a lot of big bolts, and you're taking out a lot of net section, and now all of a sudden your net section is going to govern the strength of the member, and you're going to have to reinforce the section just because of the holes you're punching in the connection. So I'm not saying you should you have to pay attention to it. And it's primarily brace frames and truss members that I'm talking about here. Does that answer the question?
Yes, it does. Thank you. Okay, I'm going to move to slide 59. This is tip 38 regarding maximizing slab span and minimizing number of beams. This person asked for your comments on this thought. What about increased beam depth and slab thickness and the impact it has on floor-to-floor heights? We seem to be fighting for ceiling space so often when ductwork is considered.
Absolutely, that's a huge consideration. If your project is such that you've got a tight floor-to-floor height, well then, you have to live with it. You have to talk to your client to see if they can get a little bit more floor-to-floor height. There's a cost that comes with everything. So they might want the lowest possible floor-to-floor height, but that's creating some inefficient. Remember at the slide communicate and coordinate. Point out to your client that, okay, we'll give you that super low floor-to-floor height, but here's the penalty. I worked on a project years ago where the maximum beam depth was 8 inches, and we actually had beam web penetrations for electrical conduit at like 12 inches on center. There was that little room in the ceiling. So there's a price architects or owners have to pay for requirements that they want to absolutely stick to. But definitely, if your floor-to-floor height allows it, you should go with the most efficient and economical framing system, which is usually a deeper beam rather than a shallower beam.
Okay. This is something of a detailing question. When designing HSS column connections with single shear plates, what do you typically do? Do you center the beam on the column or center the connection plate on the column?
We center, you know what, that's a good question. We design these all the time, but now that you mention it, I'm assuming as an engineer of record, we'll just show that beam right on the column line. I'm going to go pull out a couple piece drawings after this webinar and go see where they put the shear tabs. It really doesn't matter. I don't think it matters. I think ask your fabricator if they. But I think when we show on our drawings, we show those beams on the column grid. We generally expect that beam to be centered on the HSS with the shear tab being slightly offset. I think that's probably what they detail.
Okay. Next question.
It doesn't affect the design.
Okay. Next question is, are there any advantages of a single plate shear connection versus a single angle or vice versa?
Well, the single plate shear connection can be used for skewed connections. That's the huge advantage of a shear tab. They can be used for skewed connections. But you know what? Here's a case where you have to give your fabricator options and flexibility. By delegating the connection design, you can allow your fabricator to determine what suits them best. They might be a shop that favors welding rather than bolting, so let them use the shear tab. They may be a shop that favors bolting, so maybe it's a bolted single angle connection. So options and flexibility are the key to reducing the cost of steel frame structures. So I don't have a preference for one versus the other.
Okay. All right, here's a commenting question. Many of our clients and project managers expect to see full connection designs in the final construction documents. Do you have any advice on how to best convince other parties that it would be in the best interest to have the fabricator design the connections?
Maybe you could call your local AISC marketing representative. They may be able to present some arguments. I would just say it's what I've already talked about. By giving fabricators options and flexibility, it allows them to select the connections that are most economical for their shop. And at the end of the day, I would imagine that would be what's going to give an owner the lowest cost solution. By you delegating the connection design and doing so properly, you're not shirking your duties or responsibility. Our profession is getting so specialized. There are engineers out there now who do nothing but connections, where they're going to be able to out-design any engineer of record with regards to connection design. So if you're an engineer of record and you're being forced to design every connection on the project, you're probably going to be designing some pretty heavy connections or connections that are not as economical as could be designed by a specialty connection design engineer. So I would use that argument perhaps as a way. You're not shirking your responsibility, and the owner is not getting an inferior product if you delegate the connection design.
Okay. I think this is in reference to your tip on hanger connections. The single angle hanger connection value seems to introduce some uncertainties that could be eliminated by the symmetry of a double angle connection. Is this an area that is where the savings is worth it?
It depends on the load, and if the load does get big enough, you do have to look at using a double angle connection. That was almost a secondary comment. Why use two pieces of steel if you can use one piece of steel? If it turns out from your analysis that, I think I understand what you're saying, you're talking about the eccentricity of that load on the hanger and the considerations of that eccentricity on the design of the hanger. But for the most part, let me think about this now. For the most part, I think it's a non-issue. If your loads are substantial enough, you're probably going to want to use a double angle hanger. Plus, with the advantage of a double angle hanger, and here I am flip-flopping, a double angle hanger, you have half as many bolts at each end because now you have bolts in double shear at your connection plate. So you have to weigh the pluses and minuses of all of your design decisions that you make, and just what you might be solving one problem but creating another problem.
Okay. Thank you very much, Cliff. We do have several other unanswered questions, but we're up against it on time. Between Mr. Schwinger and the Steel Solutions Center, we will work to address these unanswered questions, and we will shoot that out as an email so that everyone can benefit from the additional Q&A. So.